Alright, hello, I wanted to have a quick video here on some logarithmic differentiation stuff, whatever this means. So let's start off with just a couple of reminders. So let's do a recall. Couple things here. So first of all, the derivative of a log function let's say log base b of x is 1 over x times the natural log of b. And in particular, we have the derivative of the natural log, which should be log base e, is just 1 over x. We can use the same formula. Natural log of e is just 1. With the chain rule, you can use this idea, and you can say, well, the derivative with respect to x of natural log of a function of x is g prime over g of x. So you get the 1 over g of x from the natural log part of it, and then with the chain rule it says you multiply by the derivative of the inside, which would give you the g prime. So that's also a useful one to keep in mind. So that's part of our recall / reminder. And also we want to remember some log properties. So the first one, and I'll do this in base e, but it's true for any base. If you get the natural log of x plus the natural log of y, it's the natural log of the product. It's the natural log of xy. If you look at the difference, natural log of x minus natural log of y is natural log of x divided by y. And the third property, if you've got a constant times the natural log, well, it doesn't matter. I had in mind it's constant, but anything times the natural log of x, it's the same as natural log of x raised to that power. Doesn't need to be a constant. I just had in mind that it was. So the idea with this logarithmic differentiation is this is a method of differentiation that can be helpful when differentiating functions involving lots of products, quotients, or powers, or combinations of all those. And the idea is that you use the logarithm properties. If you got a product of things, you can break it up. So you tend to be going more this way with the identities. This one, that one, that one. So let's look at an example here. So let's suppose we had something like y equals x squared, square root of x cubed plus 1. All of that over 1 plus 2x cubed. And that's a pretty complicated looking function. I mean, it's nice and compact there, but to differentiate, at least using our previous rules, we would apply, first of all, the quotient rule, because you've got this divided by that. And then in the process of doing that, to the numerator, you would apply the product rule and chain rule. And then the derivative of the denominator, you'd use the chain rule as well. And it's all really pretty messy. On the other hand, let's observe natural log of y. Well, natural log of that big mess there. Well, that is the natural log of x squared plus the natural log of square root of x cubed plus 1 minus the natural log of 1 plus 2x cubed. And we can use that exponent rule to bring that out as a coefficient. 2 natural log of x plus 1/2 natural log of x cubed plus 1 minus 3 natural log of 1 plus 2x. And the idea with logarithmic differentiation is now, let's differentiate with respect to x. So we apply the logarithm first, get this a little bit easier to manage, and then differentiate with respect to x. So we've got a sum that looks like derivative with respect to x of natural log of y and earlier in the video we mentioned these differentiation rules that we have, and, in particular the derivative of the logarithm, and along with the chain rule, we've got this figured out. So we've got implicit differentiation here, which is effectively just the chain rule. We've got 1 over y times the derivative of y with respect to x. Here we're breaking up into parts, break up the sum, so the derivative of the first one would be 2 times 1 over x, so 2 over x, plus so I've got 1/2 and then times 1 over this input times the derivative of the inside, which was the 3x squared. So I'm using the chain rule. Again, using that property, way back when we said natural log of g of x, the derivative would be 1 over g of x times g prime. That's what we've got there. Minus 3 over 1 plus 2x times 2. And so that ends up being 2 over x, clean this up a little bit, 3x squared over 2 times x cubed plus 1 minus 6 over 1 plus 2x. Now we want dy dx on its own. So dy dx equals 2 over x plus 3x squared over 2x cubed plus 1 minus 6 over 1 plus 2x. All of that, well, how do we get dy dx on its own? Multiply by y. But remember what y is. Y was this crazy thing up here. So times x squared times quantity, square root of x cubed plus 1, all over 1 plus 2x cubed. So, crazy answer, real complicated, real messy, but if you think about where we started with this guy here, differentiating that was going to be, it was unavoidable, it was going to be a big mess. So, having a crazy result shouldn't be too surprising. One last thing, just to wrap this up, let me show you kind of a, let me call this a classic example. Y equals x to the x. Defined for positive values of x. Now this is a weird function. It's, you might think power rule, if you want to find the derivative, because you've got something raised to a power, but it doesn't work. You might think exponential, right? Because you've got something raised to some varying power, but that doesn't work either, because both the base and the exponent are changing. So it's not a power function, it's not an exponential function. But what you can do is use logarithmic differentiation. So natural log of y equals natural log of x to the x, which is the same as x times natural log of x. And so the derivative would be 1 over y dy dx equals, I'm going to use the product rule here. Derivative of x is just 1 times natural log of x plus x times derivative of natural log of x, which is 1 over x. So that's natural log of x, the whole thing plus 1. So dy dx equals natural log of x plus 1, all that times y. But y was x to the x. Right, so kind of a interesting derivative for a pretty crazy function, but again, remember logarithmic differentiation was what we used here, and the idea is when you've got something where logarithm properties will make it easier to handle, things with lots of products, lots of powers, things like that, this would be a method to try. It ultimately comes down to basically it's an implicit differentiation, because you're going to have natural log of y equals something that, if this is going to be useful, it's going to make that a little bit more manageable using those log properties. So it's still, it's a tricky method, easy to get it mixed up, but with a little bit of practice, you'll be all set with it.